So this is our last year of this REU program, supported by National Science Foundation. But we have plans to submit a renewal request for the grant, and so we would like to ask for your help to do that. And you can help in 3 ways. One is, providing your feedback on the assessment that you're gonna get this afternoon. That's gonna be included, right, as part of the outcomes, right? The second one is that you're gonna get early next year, actually, an email from National Science Foundation asking for some information, right? Because you were a participant on the program. So if you get an email from NSF, National Science Foundation, please try to answer as soon as you get it. It's very important. They really want that information. It doesn't take more than 5 minutes. And the third way you can help is to stay connected with us, right? You're gonna get an email probably later today asking about your plans for next year. You might be thinking about graduating, going to graduate school, maybe go to work for a company, or even take a gap year. I don't know. But whatever you want to do, please do answer that questionnaire, because we're gonna summarize all the information from more than, I don't remember, more than 40 or 50 participants in the program on the prior 3 years. And so so this is all information. And also if you would like to keep working with your lab, and maybe finish a paper, work on a conference presentation, we normally have some funds to send students to present to a conference from work that you have done during the REU program. We will be happy to consider that. And also, with your graduate mentor, I think you can ask your faculty mentor also for letter of recommendation, as you apply to graduate school and things like that. So yeah, so stay connected with us. Send us an email. You know my email, Dr. Blanc, Jenny. Just say, hey, how are you? We're doing this, and let us know what's next in your career. So, Dr. Long, would you like to say some words?
I don't really have anything formal, just to thank everybody for their involvement during the summer, and hopefully everybody had a good summer of research, and we appreciate your joining our program. Looking forward to hearing the presentations today. Thank you.
Jenny?
Yes, thank you very much for participating in this program. It's been great to meet some of you in person and most of you virtually. And I hope I can see some of you next year and having more information about your success in the future. Before we started, I just want to make a little bit summary of what we have done with the REU program. So we have 10 faculty mentors between all the presentations that we have, the lectures that we have, and also with the labs, okay? We have 10 students, 2 guest students that were taking MATLAB, and a total of 11 REUs funded, and 3 assistant trainees that are also undergraduates, and 2 students that already graduate. So thank you very much for everybody. We have a total of 26 students in this program. First presentation is going to be from Chai Park. He is from Pomona College.
Okay. So, okay. Yeah, so good morning, everyone. So I'm Che, as Jenny introduced. I'm a rising junior studying physics. And I first of all want to say that it's been a real privilege to work with Professor Bao and his mentors, although there were many complications, of course, due to the pandemic and the communications that became fairly difficult. due to this remote environment. But aside from that, I think I was able to learn a great deal over the past few weeks. So without further ado, I'll get started on the biomedical applications of photoacoustic laser streaming. Professor Bao already did a very fine job explaining many of the concepts yesterday. So I don't know if I could really do justice explaining this with the master in the room right now, but I'll do my best job here. So first of all, why is this so important? Well, as you can see in the poster, since the rise in the silicon development and the increase in how the foundries were being activated since the mid-20th century, we started to see a great interest in microelectromechanical systems, or MEMS, which honestly are just a super fancy way of saying super tiny devices. And usually what that accompanies is cramming in tiny, well, bigger macroscopic components like pumps or valves or barometers into the microscale, so that they could be multiplexed more easily. So Jenny, if you could go down for, yeah, right there, thank you. As you can see in that one flowchart right there, those are the key advantages that MEMS devices got to offer. First of all, because of their small, tiny sizes, we can use low analyte volumes. We don't have to use liters of, probably liters, that's an exaggeration, but milliliters of analyte samples to get some sort of diagnostics running. Parallelization or multiplexing, or combining multiple signals into a single channel, that is much easier to do so in this small, tiny setting. Rapid detection owing to small diffusion distances, that is really only possible in these small environments offered in the microscale. And lastly, low production costs, mostly owing to the wide availability of silicon foundries that are so prevalent around the world now. And the focus of this project especially aimed around micropumps, which are very, very vital. As it says, it allows us to deliver small, tiny volumes of analytes through flow channels at very accurate and precise levels. And for this project especially, as Professor Bao discussed yesterday, we use what a newly discovered principle called photoacoustic laser streaming. And using this, we can generate novel micropumps that have, as it says in the poster again, translational degree of freedom, where we can actually move the pump around across a plane so that it's not only confined to a single position, if you will. And all of this is possible without having any moving parts like piezoelectric sensors that are pretty common in mechanical micropumps. So could you go down a bit more, Jenny? Thank you so much. So there's a rough diagram, as you can see on the left side of the screen there. And Professor Bao already did a great job explaining this, but just as a quick overcap, we can imagine, or I guess in this case, as we see on this diagram here, what Professor Bao and his lab did a few years ago was that they implanted gold nanoparticles inside this thin quartz plate. And the neat thing about these gold nanoparticles is that when struck by laser with a certain wavelength, to be more specific, 532 nanometers, the electrons on the surface of these nanoparticles begin to oscillate. I mean, the exact details of this phenomenon is what's called surface plasmon resonance, but to get into the exact weeds of that, that is way beyond my pay grade, to be completely honest. But I think that's the basic gist, is that, at least for our purposes here, due to this oscillation, the solution that's surrounding these gold nanoparticles that are in contact with this quartz plate, they begin to expand and contract through these pulse lasers. And in turn, ultrasound waves are generated. And this is what allows jet streams of fluids to be formed. So in other words, like, we can use only pulsed laser pulses to generate jet streams of fluid, and that could allow for smoother drug delivery, possibly. And these laser pulses could be easily manipulated as well, as covered yesterday. So the large goal of this project is during the summer was to investigate this further and perform further literature review to see what other applications might there be. Could you go slightly up for a second, Jenny? Thank you. It's a good diagram. This is a simulation that was performed on COMSOL, which is a very robust simulation software for computational fluid dynamics. And this shows a model of acoustic streaming where we're literally using pulsed ultrasound waves to generate this stream flow. So in a way, we can think that we're doing a very similar thing, but except that we're using laser pulses and using the thermal expansion and contraction and the intervals of that to generate this jet stream. So what could be the possible applications? You can see, could you go all the way to the bottom, Jenny? Thank you. So the more applications that immediately come to our mind are lab on a chip, precision drug delivery, and biophotonics even. So lab on a chip, we have these micropumps can be thoroughly used for micropneumatics, of course, as the name implies, but also gas chromatography, which requires very careful delivery of analytes. And for these devices without any moving parts to accomplish this will be a great step forward. Precision drug delivery. The micropumps in the past have been used for intravenous drug delivery and even extracranial delivery, which I'll shortly get into. And replacing these with these newly developed micropumps could be a great step forward in reducing production costs and potentially even investigating further ways to use these gold nanoparticles that are even biocompatible.
You have 1 minute.
Okay, thank you. And even biophotonics, optical tweezers, as explained yesterday, but also neurophotonic probes, which were covered by this one team very thoroughly over in Caltech, where we have what are called emitter pixels that shoot out these collimated beams of laser. And although it for that particular project, it was for optogenetic stimulation, I can see that as a lowly undergrad, of course, that this could easily be used to control these micropumps. Of course, like the other question is like, how can we exactly implant that? But there have been other instances that I saw that where we were actually implant this in the extracranial spaces, which constitute about 15 to 20% of the brain value. So my guess is that this could be very useful for neurotransmitter delivery in clinical settings. But these are at least some of my thoughts and speculative insights that I could do, again, as a lowly undergraduate student. So thank you so much for listening to this presentation.
Hi, my name is Ai Nguyen. I'm from the University of Houston, and I'm doing the same project with the chair, Mr. Park, and my advisor is Dr. Jimmy Bao and Chen Tong. And because Mr. Park already talked about the theory about the laser streaming, so I will focus my part in the application. And in my research, we will focus on the Python, the efficient high-level data structure, and we're using the Python to help to control the laser and how to get the data from the laser. So our main project is to control the ESP motion controller from the National Instrument and the spectrometer using only the live field software. So because the ESP motion controller is using another software, and the spectrometer using another software is the two different software. So our research is how to combine in one live field software. So it's make everything more easier and convenient. So you can see here is what we are trying to do in the. This is the okay. Sorry for my. It's not look exactly like that. So this is the laser and the laser device, and the laser will come in from the laser device, and you go to the mirror. They will reflect to the mirror, I think there are many the mirror, and at the end they will go to the sample, and before going to the spectrometer, the mirror will controlled by the ESP motion controller, and you can see on the right side, this is the this one is big motion controller, and this is you have to wear the glass because the laser is really dangerous. And this is okay. Sorry for my picture is not clear, but this is the mirror in here. So the motion here can control the mirror going up or going down like that, and you can check up the velocity or the distance. And this is, you can see one picture. Let me pull out a little bit. Oh, I cannot zoom in anymore. So you can see 1, 2, 3 here. The laser will come in from this, and this is mirror, and this mirror can be controlled by the ESP motion controller in here, and they will go to the spectrometer, and this will go to the spectrometer and get the data. So our research is to combine the software control the ESP motion here, and the software control the spectrometer into the live field here, and get the data like that. And as you can see here, if this is this is not a laser, this is, I think this is the I'm sorry, if the laser, the graph will go be the vertical, it's not something like that up and down. And we Dr. Jimmy Bao want to using the Python to code in the Python to control the ESP motion controller. And this is, I think this is from the National Instrument, it's a little bit old, and it's connected to the PC or laptop with the GPIP USB converter. And because right now we still stuck in our research is still stuck in there, because we only know how to connect the RX232 to the PC and desktop. So we have a little bit problem, right? We cannot apply our Python to control ESP yet. And I hope we can solve this problem in the next month. Assuming if we have the Python programming to control this, we can apply it into the live field software, and the live field software control the spectrometer. After we have the laser coming through the spectrometer, we can collecting and analyzing data. So our at the end, if everything will go like, we will have the live field here, control the spectrometer, and use the Python to control the ESP motion controller. So you can control everything into this. You can control this one, this one, this one, this one into one software programming. Oh, I think this. Sorry, that's on my poster. Thank you for listening.
Jocelyn Ramos from University of Houston.
I've been working on the magnetic milliscale robots project with Dr. Becker, Dr. Leclerc, and Yisang. So to start with, our issue that we're addressing is that we have a pretty big problem with blood clots, just in general. According to the CDC, I believe it's about 900,000 people annually in the United States that are actually affected by blood clots, and 100,000 that die from them each year. This is also coming up more recently this year and the last year, because blood clots are people that catch COVID-19 are actually more likely to experience severe blood clotting. So this lab has been working on designing these milliscale magnetically controlled robots that we've been calling swimmers, which can actually abrade at these blood clots. These swimmers could be a potentially less invasive treatment option than what we currently are using. And because of their small size and precise control, these swimmers could actually potentially enable new types of surgery, because they could be able to get into smaller areas of the body, like smaller vessels, smaller arteries, that we couldn't access before. And I'll scroll down and show you a bit of the design. If you can see the images down here on the bottom left, this is kind of what our design looks like. It's a small bullet shape with a helix around it. What happens is we have a small axially magnetized magnet in the center, and we have a magnetic field that is rotated around it, which causes the entire body to rotate. And because of the helices on top of it, this produces a propulsive thrust, which propels it. My project focus has been in two areas for this project. It's been in one, improving the swimming performance of these by using computational fluid dynamics for design optimization. And then my second focus has been in improving the capability of these swimmers by actually adding new tools to their toolbox, seeing what else that these swimmers could accomplish besides working on blood clots. Now this image over here with the magnet in it, next to it, we have this image on the left for this box. This is a design I've been working on that we could use for deploying some type of second piece, which is this third image over here. And this could be some kind of piece that is left behind and can slowly dissolve over time, some kind of drug that could work on dissolving blood clots or some other type of targeted drug delivery. Over here on the left, the image is both of those pieces combined. It goes in and it leaves behind the third image, and the second image is the one that retreats. And I actually have a video of this that I can show you. I'll have to scroll out to show it to you though. I think it, there we go. And that's the first design of it. Obviously, it won't be this big. This is a much more scaled up version so that we can actually see how it works. This model is 60 millimeters by 25 millimeters, and the actual models that we would be using would be, I think the biggest ones would be around 6 millimeters by 2.5 millimeters, and they could be made smaller as well. So the project goal for the summer was to create a precise, safe, and functional method of delivery for a drug-eluting device, or to work on one at least. Find the best possible swimmer designs depending on the tasks to perform. And then for objectives, it's explore the capability of milliswimmers in use for various biomedical applications in the body, establish a pipeline for simulated design testing of the swimmers, develop a reliable method of simulating the propulsive thrust of these, and to design and test new swimmer tool mechanisms. Now, on the software side of this, we've been working for a while. I've been working since before this program started, so that's why there's this much information on it. But we've been working on creating an automated pipeline for designing these swimmers for different applications. And it kind of starts where we have some kind of draft design. We're using FreeCAD. We edit the mesh files for these designs using Blender. Then we put it into some kind of CFD software for simulation. We're using ANSYS Fluent. Then we get the information from it from post-processing with peer review, and we use that in order to optimize our design parameters in MATLAB. And that again goes into a loop for the design. This isn't a completely closed loop yet, but we are working on it. And this summer I've been working on the simulation part of it with ANSYS Fluent. Now, a lot of things affect the design. Our design parameters could be pitch, tip shape, thread depth, surface texture, buoyancy, and magnet strength. Those all influence the performance of the swimmer itself. And over here I have an image you can see is this larger tube with a swimmer inside of it. This is simulating the walls of a section of a blood vessel where we have a constant velocity inlet, pressure outlet, constant velocity moving wall. And the swimmer itself is actually stationary inside of this, but moving relative to the constant velocity boundary conditions. It also has a rotating cell zone interface where the whole thing rotates, and then the program adjusts for that cell zone interface in the actual results. Over here on the left, we can see from that simulation, we got the pressure magnitude plot and also the velocity magnitude for a swimmer rotating at, I believe, 400 radians per second. And then from that, we can compute the thrust produced by one of these swimmers in each rotational frequency or rotational velocity, I mean. And then we can plot those curves and find the force that it's needed in order for one of these swimmers to hover when it's facing straight upwards like this. This horizontal line is what we call the vertical static force, which is the difference between the buoyancy and weight of the swimmer. And so the intersection of one of these curves with this horizontal vertical static force line actually tells us what is the frequency that this swimmer needs to rotate at in order to hover in place. So this has been really exciting to work on. We're hoping that at the end of this, we should be able to have a functional CFD model and validation data to check it with. We should have new swimmer mechanism prototypes and draft files for it. And farther in the future, hopefully, we should have this pipeline for the automation of the optimization of these swimmers. That should be a completely closed loop. Are there any questions?
I have a quick question.
Yes.
How are these removed from like the blood, or do they just dissolve?
Oh, I guess that was a bit confusing. So the swimmers themselves, they can get in. I mean, they rotate in order to have a propulsive thrust, which is their main method of navigation. They can get inside of the body, but they can also rotate backwards to have a backwards propulsive thrust. So they go both ways, and they would be small enough that there shouldn't be an issue with them getting stuck. The part that I was talking about dissolving would be the second piece over here under Project Focus 2, where there can be something that threads over it and that can be made of some kind of dissolvable drug, so that it dissolves over time and it helps with other problems.
Well, thank you for a very nice presentation. I see you have working on closing the loop in the lab, 5 different type of programs. What have been the challenges for you? I guess you are working on the simulation part right now, right? But what has been your experience with the other parts of the loop? Yeah.
I've actually, I guess I could say I've had a lot of challenges. This summer specifically, it's mostly been in the hardware, mainly because we don't have access to the printing services that we usually do. I think they actually stopped printing because of COVID. I'm not sure if they're going to resume again. But because of that, I've actually been printing much larger scale models of it in order to test the mechanism that it would use. So I've been kind of limited in how often I can create prototypes for that. But usually that wouldn't be the same. Usually we could print high definition models that would be a lot smaller without worrying about the wait time from sending our prints up and getting them delivered from someplace far away. We were using the NSM print shop for that.
I see. So what is the material that you use? Some type of ABS plastic or something like that?
We've been using PLA at the moment. I'm not sure if our actual models that we would be using, I mean, for our prototypes, we've been using PLA, but I'm not sure if it will be made of something else when it would actually be used in vitro.
Because if this is intended for a medical application, you probably want something that is biocompatible, right? So that restricts the materials available.
So it's both material and, I'm sorry, Dr. LeQuick has actually been collaborating with another lab, working on ways that we could also work on the biocompatibility. One way is actually coating the swimmer with different materials. We could do a coating of gold, actually, and that would make it more biocompatible. But we're also working on tests as well to check the biocompatibility for if it breaks up the blood cells or if it breaks up blood cells when it's operating as well.
Okay. So what are your plans moving forward?
Well, there's a lot to work on for this project. So I plan on, as much as I can, finishing up the simulation part of it. Hopefully we can get access to better printing services soon, which would allow me to keep working on the drug-eluting device part over here, that's on the left side. For now, it's mostly just continuing my work with the simulation for ANSYS Fluent.
Well, thank you.
Anthony Gutierrez, and Peter.
So I did work with the Knuckle project, in particular the AI model. The Knuckle project as a wider project aims to explore the neural basis for creativity through the combination of live as well as neurodigital interactive art, artificial intelligence models, closed loop brain computer interface, and mobile brain body imaging technology. Generally though, the portions of this I'm more concerned of are the live art demonstrations where our artist Geraldina is going in, painting, we're collecting the EEG data, and I'm working with the AI model that's working to take the gathered data from both the EEG and the paintings themselves to try and make a GAN network that can recreate art using those two things. The future possibilities for the project as a whole, there's unique opportunities to bridge fields of AI, arts, neurotechnology, neuroscience, with use of art therapy, and there can be further understanding of the capabilities of artificial intelligence. If you're interested in the artists, there's a little QR code here you can scan. That'll bring you to our website, shows some interesting pieces. And if you're interested in the Nahal project, more so than I'm gonna get into here, there's also a QR code here that'll bring you to the Nahal website. Yeah, so to sum up what I'm working on, I have a project statement here, but I also have a piece of her painting. The main concerns for what I in particular working on were developing a deeper understanding of the style GAN model and how it operates, because that's what we built our generative adversarial network off of. Creating a solution for an issue with maintaining one-to-one representation between EEG data and the artwork, because we have limited amounts of art samples to feed into the network, but we also need corresponding EEG data for training. And also developing methods to make the most out of the EEG data points, because there's a limited input for what you can actually put into the GAN network. Like you can only have like 512 data points for the latent space representation, which is what we're using to feed in our EEG data. To work on some of these issues in relations to goal 2, I made a Python script that is using a couple packages that is essentially taking the video and allowing you to designate a space where the artist canvas is. And it runs through the video, and whenever the canvas isn't obstructed by the artist, it'll give you that frame. And that's helpful in taking the live performances and extracting the physical information for them for the GAN model. If I have extra time, I have a little demonstration video that just demonstrates that use. And then in relation to goal 1 and my efforts in understanding the GAN model, I have a chart here that kind of goes over the process that I can just walk through. Yeah. So we have pre-processing the EEG data, in which we downsample the EEG data and run it through a filter, essentially to cut down on bits of information we wouldn't want, like if the artist bumped their headset and there's a big spike, we don't really want that data, or if there's like some other movement, it can just get rid of the abnormalities and information we wouldn't want. The EEG data is flattened, it's normalized to a standard deviation of 1, and it's applied to the mapping network in 8 layers for the generator for generating images. For the GAN network is kind of divided into 2 portions as a generator and a discriminator. A generator will generate fake samples of artwork, and the discriminator will compare fake samples of artwork to real samples of artwork to compute a loss. So the AI model learns through competition. The generator tries to trick the discriminator, and the discriminator tries to discriminate between the real and the fake samples. So yeah, once the data is adapted for the model, the training begins. It begins with a 4x4 training. So in order to generate high resolution images, it starts with a very, very low resolution image, like literally 4x4, like 4x4 pixels. And it'll train with that for a while. Then it'll move up to 8x8. That'll move up to 16x16, 32x32 to a 5x12 resolution image. And the latent representation data, the actual EEG data, is added in 2 portions for each section here. And if you notice, we also add in some Gaussian noise, and that's for some stochastic features. Like the StyleGAN model originally was designed with the intent of making like people's faces and such, and the stochastic features would be like things like freckles or hair direction or little bits of randomness that you wouldn't necessarily want to be controlled. Yeah, I have a bit of time. I'll show my little video demonstrating the Python script. Here, can you see this fine?
Yeah.
Excellent. So yeah. Oh, shoot. Really? Yeah. So whenever you launch the program, it'll ask you to find an MP4 file, and it will, for the video itself that you want it to read through, it'll ask for an output folder. It'll make one. You just give it a name. It'll ask for frames per attempted image. So like if you want to check for a frame like every 60 frames, like if it's a 60 FPS video, you get one every 60 frames. It'll be for each second. Once you do that, it'll ask you to select the bounds for your canvas, and it'll pretty much try and make a square that's parallel to each side of the screen. It'll go through, it'll analyze all the frames, and once it's finished, you'll get your output. You'll get all of the frames where she wasn't obstructing the image. You'll notice, it'll give you the frame number. You'll notice there's a couple frames missing, and that's because there's a frame where she is in front of the canvas, so you don't have a frame for that instance. So yeah, in summary, I have a Python script that helps to helps to extract images from the videos and allows for better one-to-one matching between the art frames and EEG data, because we can correspond the EEG data times with the frame times that were extracted from the video. And I also have the diagram that helps represent our rendition of the StyleGAN process and provides a good point at which we can improve upon and modify the model in the future. So yeah, that's my presentation.
Okay, any questions? Thank you, Anthony.
Oh, I do have one question. So I'm kind of interested on how you specifically made it in the program to recognize that Geraldino wasn't framed. Was it like a specific like when she would like go into the frame, would it be like if it was like a disruption in like the color, or like how was that? I'm just a little interested, and you don't have to go too in depth on that.
It's working off of movement detection. So if
Okay.
it detects movement within the bound area you selected, it will flag that frame as something where she is in front of it. Because
Got
like
it.
there's instances like Geraldine uses like a bunch of different things when she's doing it, and there's like some frames where just a rake was in front of the image. So yeah, it's just based off of movement detection.
Got it. Cool. Thank you. All right, so hi, I'm Ava Nelson, and I was able to participate in the Art Science AI Neural Basis of Creativity section, basically, which was a ton of fun. And I'm based in the College of Technology at the University of Houston, and I'm a biotechnology major. And then my faculty advisor was Dr. Contreras, and my grad mentor was Akshay. And so just to kind of like introduce what I was working with, the neurotechnologies for art for the Brain Lab mostly focuses on the use of neurotechnology in aesthetic and artistic spaces. And so some of the previous projects that the neurotechnologies for art section has worked on include the integration of neurotechnology with video games. And so it was a little while ago, they had kids play Minecraft and recorded their data from that to kind of work with that. And then also art therapies and human-linked smart architecture. And so what I was able to specifically help work on was Project Nahal, which was basically, Anthony went over this a little bit earlier, but our goal is essentially to be able to create paintings in junction with our artist Geraldina using a deep learning AI, and then training the AI to better understand the style of the artist, essentially. And then I also got to work on the Brain on Dance workshop, in which we recorded dancers' brain activity while they were doing various activities to better understand the connection between the dancers and the music, and just to kind of show a deeper connection between the arts and the science itself. So to kind of look at our focuses and the industrial relevance, like I said earlier, we've really focused on kind of like the intersection of art and science, and like more specifically art and neuroscience. For Project Nahal, we mostly focused on understanding like Geraldina's creative process. If you check out some of the videos on the Project Nahal website, it's kind of interesting to watch the performances, because the AI will generate the images as Geraldina is working on her paintings, which kind of shows like her creative process, essentially. And then for the Brain on Dance workshop, I was able to work with those dancers to better understand the inner workings between dance and music, as well as like the science behind that. And the main need for this intersection is often this isn't like explored a lot in the field of science, and being able to understand this better can aid in rehabilitation for those who may not be able to make art themselves, or maybe used for those who want rehabilitation for mental health or anything like that. And so for Project Nahal, the way that our data collection essentially worked, and I was on the data collection team, so essentially I was to help with setting that up and making sure that everything was done properly. We begin by collecting EEG data, and from our artist, Geraldina Wise, while she's looking at her own paintings. And so this is done before any of the 15-minute performances that we will have later. And it's done in order for the AI to have more information to better understand her own style of painting. And we were planning on having about 8 to 10 sessions of that to make sure that we had as much information as we possibly could. And then during these 15-minute performances, the AI generates a painting and basically uses Geraldina's EEG data and the previous data it's received from those previous data collections in order to more accurately replicate essentially her creative process. And another part of the 15-minute performance includes sonification, which is essentially having her EEG data converted into sounds. And so this works by having specific grammars, or basically like different wavelengths of the EEG correlate to specific sounds. And a lot of these sounds were done by the Emmy-nominated composer Amos Cochran. And while we were planning on working on Project Nahal this month, unfortunately, due to some timing conflicts, that's been postponed to next month. But until then, I've been able to work on the Brain on Dance workshop, in which I was able to help set up the data collection for our dancers. And how that worked was we had 4 days of data collection, and we essentially did like the same kind of trial every day with 2 different dancers from the dance group. And so how it worked was we would gel the participant, which is essentially here. Sorry about that. Let me just zoom out a little bit. There we go. We would gel the participant, which you can see in this image right here. And that's essentially just setting up the EEG cap, making sure that the electrodes are able to properly collect the data from the brain. And then we set up, it's out of frame here, but we have a system that is able to wirelessly receive the EEG data from our participants. And so that allowed the dancers to be able to move pretty much freely while we were able to collect their EEG data. It was actually really important for us to make sure that we would note important times in that EEG data if there was like a specific event that the dancers had or anything like that. And so while I was aiding with data collection, I made sure to include that. To go over the specific method that we had, how it would work is we would begin by having the artists sit still, have their eyes closed, and they would listen to the music. And then after that, when the music was complete, the dancers would then dance with their eyes closed to the music. And we were kind of having them focus on like visualizing internally how they would move with that music. And it was completely improvised with no like previous rehearsal for those. And then they would dance with their eyes open with a partner. And that partner would also be one of the participants who was hooked up to the EEG cap. And we would have them interact with each other and have them essentially improvise a dance in which they would try to work with each other. And then for our final one, we would have them rehearse with a group and then practice a new dance. And we wanted to kind of get like a better understanding of like what the creative process was for that. And so for our project goals overall, for Project Null, our main goal was basically to better understand like the creative process and also be able to potentially get into artistic therapeutics in the future. And then for the Brain on Dance workshop, our main goal is to basically like both represent like the intersection of both the science and the arts and to better understand like the interactions of the dancers with the music. And being able to see that could potentially help with any kind of like rehabilitation in the future related to music or dance. And then also kind of just in overlapping the two, myself and a few of the high school trainees were working on an EEG data collection manual to aid people in collecting EEG data in the future. It is kind of complicated, especially if you've never done any kind of data collection before. And so making sure that people are familiar with the gelling process, as well as setting up the receivers for wireless EEG data collection and the proper software usage to make sure that the information is recorded is all being put in a manual so people can use that in the future. And then for the end of the program, we're expecting to be able to have this EEG data collection manual to be out to other members of the Brain Lab so they can be more familiar with how EEG data collection works. And then we also, after completing the first Brain on Dance workshop, we were able to create like a more solid foundation for more workshops in the future, and eventually a performance in Washington, DC in April, which will be quite great. And I think that's all I have to say. Yeah.
Okay, thank you, Eva. Exact. Okay, any questions?
What was your favorite part about working on the project?
I would definitely say like being able to get like a hands-on experience with the data collection, being able to help set up the gelling was really interesting to me. And also like being able to like gain a better understanding of like how EEG data collection actually like works. Like it's not you just put on the cap and you're good to go. You have to make sure like the electrodes are actually able to receive the electrical information from the brain. And so you have to use a saline solution to be able to conduct that. And I always thought that was like really interesting. I never realized that there was so much important work that went into making sure that that all went properly. So.
So hello everyone, I'm Carolina Ramirez, and this summer I worked on optimizing the placement of Electro-Oculog sensors. So as we know, EEG signals tend to be very, very noisy. So denoising is very crucial for accurate EEG classification, especially when you are using dry electrodes, just because there's a lot more noise than when you are using wet electrodes. So just a quick reminder as to EEG classification. Basically, EEG classification helps us understand what frequencies are most prominent in our signal. This includes presence of noise or, what part of the brain is active, which we do by extracting features. So, for example, my team, our long-term goal is working towards stroke rehabilitation. And so what we want from our EEG classification or EEG feature extraction is to detect motor intent. But if our signal is very noisy, we'll be impeded. We won't be able to get that detection of motor intent done. So in particular, for channel restricted dry electrode EEG applications, you really rely on advanced EOG removal algorithms. So again, let me break this down a little bit more. So a channel restricted application just is context-based. It just means you, for some reason, want to have a certain maximum number of EEG electrodes. So, kind of delving a little into, industrial relevance here, it's just all about the sort of technology your team wants. So, maybe in a hospital setting, this could be that you want to create a simplified EEG headset or EEG cap where you need rather than have a lot of people on a team help put on the EEG cap, you just need 1 or 2 people, and then the rest of the team can focus helping another patient. Or it can just go down to cost. Each EEG sensor is very expensive. So if you want to reduce costs, you gotta, simplify your system all around. So those are just some examples. However, the relevance of this is that you're not just focusing on how many EEG electrodes you have. You also need a certain number of EOG electrodes just for processing and filtering your signals within your algorithm. So, what is an advanced EOG removal algorithm? There's many different types. It can be a machine learning or a deep learning system, and it can also either run in real time or not. So with that kind of introduction said, let me delve deeper into what I specifically worked on. So as I said earlier, I'm working on optimizing the placement of EOG sensors. What this means is that the first time that we collect data from our participant, rather than follow this typical 4 EOG standard and just put 4 eye sensors on, we put 6 eye sensors on their face. And with this, we can then, create our own configurations, which we did 14 different configurations, and tell our algorithm, tell our program, hey, pretend as if there's only 3 electrodes, for example, and filter the signal that way. So that's just a figure explaining that. So let me piece it all together by showing the signal processing pipeline. The first step, again, as I mentioned, is you collect the raw EEG data with all 6 eye sensors on, just some basic pre-processing filtering, just resample to 100 Hertz and apply a high pass filter. And then you get into more nitty-gritty filtering with the H-infinity adaptive noise cancellation. And I'll explain that in a second, but what you need to know right now from this figure is that the output is not just a filter signal, but also what is called noise representations. And then with these 2 variables, you could say we can perform our data analysis. So our long-term goal is to minimize the number of EOG electrodes that the H-infinity algorithm uses. So something very important to keep in mind here is that we can't just be like, oh, I want my system to have 1 EOG sensor. That would be perfect. Well, no, you still need to compare it to the standard, to the 4 EOG setup I showed earlier. And so H-infinity is a real-time machine learning system. It, as I said earlier, really helps us accurately filter our signal. And that's why we need to have that comparison to the ideal case. So I've probably said a lot by now. You're probably curious as to how the EOG sensors actually tie into the H-infinity. So here's like a little quick breakdown of that. So the first thing H-infinity does is at this point, you've input your original EEG signals, and you use a formula to calculate what is called the noise weights. And the noise weights come from the particular EOG configuration you have chosen. Then once you calculate the noise weight, you multiply that by your original EEG signals to get the noise representations. If you remember, that's one of the outputs we need. But from here, to really filter your signal, you have to get your original signal and subtract the noise representations from that. And that's, the very basic math behind that. So it's obviously a lot of small steps to get to just choosing the best EOG setup. So the first thing I had to work on is my project objective, which is just characterizing the noise removal ability of all the 14 EOG configurations I showed earlier. So the way we analyze that is we really need to get a lot of eye artifacts, a lot of blinking and stuff. So it's just a 15-minute long experiment, and the participants just follow arrows moving across the screen. And then moving back to the actual data analysis, we actually did 2 different types of data analysis to not just rely on one system. The first one was the root mean square error, the RMSE. And what we do is, by definition, the RMSE kind of compares the EOG configuration you're looking at to the standard. So we just get a bunch of values. So every 15 seconds, over 15 minutes, a lot of data. So we just want the mean of that to get just one value. And then you also have your signal to noise ratio calculation, or SNR. However, this one by definition does not create any comparison to the standard. It's just the SNR of one particular EOG configuration. So we have to find the SNR of the 4 EOG standard, and as it shows right here, subtract that from the SNR configuration, from that configuration we are looking at. And we get what, it's called the SNR difference. Again, we get the mean of that. So, a lot of talking probably. So here's a figure to show that. We have all the 14 configurations labeled here. Their mean RMSE and mean SNR difference. What we're basically looking for is the lowest RMSE and SNR difference values. So we can see we have like 3 points here that really kind of meet good standards. But I did only label configurations F and G. Now, the point of that was that as part of what my team is working on, our very long-term goal of helping for stroke rehabilitation, my team is creating a custom headset. And, we don't want the patient to have an eye electrode right under their eye. That would be very uncomfortable, which configuration A relies on. So instead, we think F and G seem to be, very good options. So from here, we can now go on to our next steps. So there's actually kind of two directions we can go in this. The first one is looking back to our H-infinity system and optimizing how we calculate the noise weights. So I mentioned earlier, the noise weights are calculated from an equation, and that equation has two constants, the H-infinity learning rate and the gamma constant. So you can just play around with those values. Do the same comparison I explained earlier with the RMSE and SNR difference and see if it is still configuration F and G, for example, giving you the best output. So you can do that. The second thing is working more on the headset, so the channel restricted dry electrode. To do that, the plot I showed earlier was just sample data from one participant so far. We need, comparison across all 10. Yes, thank you. So we want to run a lot more, trials, a lot more experiments. And at this point, it would be a little bit tedious to compare all 14 EOG configurations for all 10 participants. So instead, maybe we can choose our top 2 or 3 configurations. So maybe keep configuration F, configuration G, and maybe choose another 2. And then compare those few EOG configurations across all the participants, run analyses, and then we can finally reach our end project goal to just finalize which are the best EOG sensor locations. So I think that is about all I have to say from my presentation. So I'll zoom out in case there are any questions.
I had the good privilege of working under Dr. Liu. So starting off research this summer was pretty exciting. It felt like I actually had an impact on decisions that were being made, and we had been making good progress. So I'd like to thank Dr. Liu, for helping me out with this research, and then also Vishal and Ranjia for just being there for me along the step of the way. At this point, I had been focusing and studying light-driven microfluidics with laser streaming. So I know that Che and I also explained a little bit about some of these phenomena before, but in case y'all forgot within that time, I can give y'all a refresher. So our actual objective of this project is to see if we can analyze or create a more simple method of fluid motion control without the use of machinery such as pumps and valves, and maybe turn towards something a little more simpler. And so this is where we talk about light-driven microfluidics. So this is one of the most recent developments in fluid motion control. So there are different phenomena that are of use regarding light-driven microfluidics. So on this chart right here, you can see, so they make good use of photon momentum as well as the thermal energy and photochemical energy. And taking good use of these different phenomena can help us manipulate or alter fluids in different ways. For example, if on the very left over here, you see there's 2 liquids, the orange and the blue. If these 2 liquids, which have an interface, if they have a different refractive index, when a laser is shined in between them, then it creates this dip. It creates this radiation pressure, right, which creates the motion of the fluid. There's also a phenomenon known as optical tweezers, in which you can have a focused laser on an actual object within a fluid, and then to some degree be able to control its motion, right? And then taking the use of capillary forces, as you can see here, there's a surface tension gradient on this water droplet in which the laser is shining on just the left side of the droplet. So if you look, the theta on the left, there's a greater contact angle on the left than the right, which means the surface tension is higher on the left. So this also creates motion. And then lastly, there's something called the Marangoni effect, which can sometimes happen. And so what this is I think it also has to do something with a surface tension gradient. This one I remember I need some clarification on. But so the basic idea is when there's a beam applied to a fluid, you can, through some phenomena, you can create a fluid motion. So the advantages are obviously contactless stimulation. You can tune it relatively easily, but there's a lot that can be improved upon regarding practicality, and then actually creating a more robust system of maybe having a little more control over the actual fluid motion. So this is the part that I'm focusing on. So within light-driven microfluidics, this phenomena specifically is laser streaming, right? So the basic way it works is there is a plate of metal inserted into a container of liquid, right? It's fixed onto some quartz and it's inserted into some liquid. And then when a laser pulse is shined onto that metal, it very rapidly expands. There's a very rapid thermoplastic expansion. And that expansion actually creates an ultrasonic wave through the fluid. As this ultrasonic wave attenuates, all this sound energy is eventually converted into mechanical energy, which is then shown in the form of a physical wave in the water, right? So when I first was reading up and studying on this, this seemed like sci-fi to me. It was like, oh, I'm shining a laser at some metal and then I get this jet in the water, you know? And so I thought it was pretty cool about also kind of how simple the process seemed. So personally, I thought that was very interesting. And so I mentioned the metal plate being used inside the container, but there has also been a similar study. I think Dr. Bao mentioned this earlier, where they actually had gold nanoparticles inside the fluid instead of the metal plate, right? And so, so to keep going, what exactly is the goal here, right? So one of the clear goals is to research a potential photoacoustic method of fluid motion manipulation, right? So within these light-driven microfluidics, obviously, photoacoustic fluid motion is, it's a little, like, it took me a little while to understand when I was first reading up on this stuff and when I was first researching. But as Runji explained to me and Vishal, my mentors, there's certain equations that you can derive up here, and then through first order and second order derivations, you can actually calculate and kind of estimate the motion of the fluid. So there's both, in the jet, there's both oscillatory and non-oscillatory motion, right? So what that means is, I wish I could put a GIF on this poster, right? But it was a PDF, so I was like, I guess I can. But the basic way it works is, if you imagine a wave like on the water, right? It looks like the wave is moving. Let's say if I drop a pebble into the water and then these waves propagate out. You can see these waves moving, but if you actually think about it, one particle of fluid or one fluid particle might stay in just one spot, like it doesn't move. It may move like back and forth within its area, or it may move up and down. But other than that, it doesn't move from its spot. So that's kind of how you can think of a wave as having two behaviors, in which you see the physical wave propagate, but what you can't see is the particles that actually just stay in the same place, just bobbing up and down. And so I thought that was pretty interesting, right? And so some other project goals are to study in depth the phenomena that are used in laser streaming, and then also look into Eckert streaming flow and its applications. So there are 3 different types of acoustic streaming, right? Meaning 3 different types of flows whenever you have any sort of acoustics related to fluids. So the one we were focusing on is Eckert streaming, right? So this is displayed by this black and white image up here. This is like a jet-like motion in a non-uniform sound field, right? So it's pretty much what it sounds like. It's just a jet of water, right? So that's Eckert streaming. Rayleigh streaming is a vortex-like motion within the actual bulk of the fluid. So it's the vortex-like streaming that's not within the boundary layer. So on this diagram right here, this would be the red circles you could see with the arrows, or the red arrows. The last one, the Schlichting streaming, this is still vortex motion, but it's within the viscous boundary layer, right? And so this is much smaller than, at a much smaller scale than any of the others. So what are actually some of the methods and some of the stuff that we focused on through this research? So one of the focuses was to confirm that these acoustic waves that later transform into mechanical waves we needed to confirm that these waves are actually created by the thermal expansion of the gold and not direct laser heating of the liquid, right? So just verifying the source of these waves, making sure like it is actually caused by the expansion of the gold and not the actual water or whatever else fluid heating up. Next was to actually derive the equations that explain the motion of the water or the motion of the wave through the water. So kind of briefly what I explained earlier. So you'll see some harmonic and some non-harmonic motion. And then also identify the 3 types of acoustic streaming and which ones are more important towards our research and towards the goals that we want to go to. And then also just running simulations and comparing it with our experimental data, see if anything matches up. So I have these 2 diagrams right here of COMSOL simulations that maybe a little more accurately show kind of what's going on, right? So over here on this left, you can see as the, this is a simulation of the metal plate actually getting hit with a light, being expanded, and then creating this.
1 minute.
Okay. And then actually creating these waves, right? These acoustic waves. And then so you can see there are areas of high pressure and low pressure, and then these are propagating through. Here on the right, you can see another simulation, and this actually shows this is the Eckert streaming, right? Which it's a jet-like motion, right? And then so what's the expected impact of all this? And what are some deliverables? So obviously this has lots of great applications in fabrication methods, tech, medicine, anywhere in which you need a non-invasive way to move some fluid simply with just a laser and a piece of gold, right? So some of the goals are to reduce current costs of uses, learn how to gain more control and precision over laser streaming, and perform some more tests to verify our results. And that's pretty much it. Thanks, y'all. You have any questions? Cool.
Thank you. Jacob is from University of Massachusetts.
So my project this summer was designing an adjustable Dry Eeg headset. So Dry Eeg headsets have significant advantages over Wet Eeg headsets in regards to setup time and the amount of training you need to operate them. But proper electrode contact becomes a problem because there isn't any conductive gel serving as a bridge between the scalp and the electrode. So you need an easily adjustable sizing mechanism for the headset to compensate for not having that bridge. So you just want to have it fit very well to the head so that there's better contact. And optimizing such a mechanism would allow for further commercial applications of Dry Eeg systems, making them available for consumer use in diagnostic and therapeutic purposes. And so my objective was to specifically develop and build a prototype for easy resizing of a Dry Eeg headset while maintaining electrode contact. And I was working with an existing model, and I was just modifying that. And so on the left here, this figure, I have a sketch of the main components of the original headset. So you have a band that goes over the head, a band that goes on the forehead, an arm with another EOG sensor that would go about here, and a lace that would be used to tighten the whole thing. And that ran through the band in the forehead. And it came back around to a unit in the back of the head, which had a spin buckle lace, which is essentially a dial that you turn and it draws the laces in to tighten the headset. And most of the modifications I was working on were regarding how to deal with the laces. And so the routing system, rather than having them run through the whole headset, it would just run, sorry, it's scrolling slow. It would just hook through on the attachment point right here. And so running them through the whole headset wasted a large length of the laces, and it would use up space for wiring because we would have sensors along this band and we would need the wiring space. And so routing them around the back unit like this would solve those problems. We call this the looping model, but although it would require some extra parts, which is just these channels. And then the other component I was working on were the sheaths for the laces, because we needed to cover them to preserve the system and have it last longer, be more durable. Although the laces would need to conform, or the sheaths would need to conform to the lace length, and so they can't be rigid. And we also have to factor in the ease of installation because, for example, we have fabric here and leather here, and the leather was actually quite hard to install because it just came in a strip and I had to sew it into a sheath, which took a significant amount of time. And so again, my goal was to improve the existing Dry EEG headset for clinical applications. And I have a list of the materials that I was working with. So the BOA system, which is just what we call the spin buckle lace, it's the brand we were working with, and it's a more concise name to refer to it as. The one in this model is one that we already had, and we did buy some backups, which we chose based on availability and shipping time. And the channels right here that we use to run the laces through, we had a plastic option and a fabric option. The plastic we ended up going with because we had it in lab. It was easy to put onto the headset and it had very low friction when the laces needed to move. And the fabric channels, we would have had to purchase them, and most importantly, they would have had very high friction, which would disqualify them as an option because we need this to work very fluidly. And so the sheath for the laces, our options were leather or fabric. You can see that I have both of them in this model. The fabric was by far easier to install. We just had a length of, it was actually a chain cover that we purchased. I just cut a length of it and put it on here and it worked just fine. And the leather is quite a lot sturdier in terms of material properties. So it protects the laces better, but it can only cover one side of laces. It doesn't conform to the length as much, or it doesn't do it as well. You can see that it like bends out. And again, it's much harder to install. So my steps for building this prototype were to glue the channels, the plastic ones, to the headset, cut the fabric and the leather, sew the leather into a sheath, which was, it took the longest out of all these steps, and thread the laces through both the sheaths and the channels, and then glue the sheaths to the main headset. So these are rigid attachments, the fabric sheath here and the leather sheath here. And so what we have as a product is a working prototype with an improved size adjustment system that prioritizes ease of use, and it has sheaths to protect the laces. It came to a total cost of about $70, but that includes a lot, that cost includes a lot of material excess. So like this fabric has about 9 feet of length, and I only used like 6 inches of it. So a lot of the excess can be used to make more headsets. And so the expected impact is that the headset fits a wide range of head sizes, which reduces the need for multiple sizes of headsets. It can be a one size fits all in the best case. And most importantly, it can be operated with one hand. And that's a big deal because this headset is going to be used by people who have physical impairments, for example, stroke patients. So if one hand is very hard to work with, it would be very important that they would be able to put on the headset and then tighten it with only one hand. And that makes it much more appealing as a marketed product for therapy, for stroke rehabilitation, for example. I think that's everything. So that's all I have.
Thank you, Jacob. Any questions?
Thank you, Jacob. So what would be the next steps in terms of evaluating this design? I'm assuming that you try it down yourself, perhaps, or some other people in the lab.
The original headset that I modified actually relied on the string running through the headbands to keep the forehead part on. So there's nothing actually like attaching it. And my head is a bit too big for that model. So when I try to tighten it, that part just comes off. But I think adding some glue would be perfectly fine there. But the main drawbacks of the model that I have, the prototype that I have itself, is that it's more or less unoptimized. It's just kind of a showcase of how looping the strings around would work, and proof of concept for the sheaths. So I guess the next steps would be designing a more optimized model of the headset with those features.
So that part of the headset, which is plastic, could be physically stored connected to the to this band, right?
Yeah.
Okay.